Guys, good day. Sorry, we had some small technical issue. How do you read me? And do you see me?
5.
Hi. That's very good. That's very good. Okay, you apparently already had the lessons on communication, as I see. Readability 5. Great. Okay. Guys, how many people are normally in the class? Maybe you remember, because I like to understand whether we have all of them or
It's usually this many.
this many. Okay.
Yeah, up to 30.
Great. Then we will start. In order not to lose the time. Okay, I'll present the my screen. Okay, so that should be visible now. Yeah.
Yeah.
Great. So the meteorology, we'll have 2 classes dedicated for that subject. The first class, we will speak about general principles, the physical processes behind the meteorological phenomena that are present in our atmosphere, and will gradually come to more practical application. The second class would be about the practical application. I mean, about meteorological phenomena that you can see in your day-by-day life. But in order to understand them fully, we need to go through the theoretical concepts behind physical background. This is what we have to clarify. And since the meteorological phenomena as we know them and that which are applicable to us as a pilots are happening in the atmosphere, we will start with the atmosphere and composition of this atmosphere. So what is the composition of the atmosphere? And what is this? So this is certain layer of gases, yeah, as it's written on the slide, that is held by the gravitational forces, which are characterize our planet. These gases, they are the composition of the atmosphere, like the gases that represent the atmosphere are the following. Here is the table. So by the percentage, the biggest contribution to our atmosphere, its weight, brings the nitrogen, which stands for 78.09%. However, that preciseness, we can leave it aside. Yeah, 78%. 78%, this is the nitrogen. For us, like the gas is, we don't interact with this gas as humans. Yeah, it is changing, but it's like generalized. There was a comment whether the amount of the CO2 changing. Yeah, it is changing, but it's the generalized table which shows you average. So on average, it is like this. So 78 stands for nitrogen, 20, almost 21. the oxygen. This gas is important for us because this gas is required for our functioning as human beings, plus combustion, fire. The fire cannot exist without the oxygen. So in terms of aviation, all those reciprocating engine, jet fuel, burning, this is all because of oxygen. Generally, yes, this is like the most widespread questions on the exam. It's like 78% nitrogen, 21 oxygen. Yes, you're right. The argon, carbon dioxide are, as you can see here, only contribute up to 1%, and there is also other gases which we call the trace gases because they are so rarely can be found in the amounts in which they can be found in the atmosphere are so low that we mention them, but like for meteorology subject, you can consider them irrelevant. Just for general knowledges, those are neon, helium, carbon monoxide, sulfur dioxide, and so on. But there is one among those trace gases which is important, which is the main contributor into all the weather phenomena that we see as we know them, like those clouds, precipitations. This is the water vapor. So the concentration of the water vapor in the atmosphere is far less than 1%. Even less than percent. However, without this, there will be no rain, or there will be no clouds. So it's small amount, but it's very important to know. Okay, so this is the general composition. And since the atmosphere is composed of the gases are in turn, those gases compose of what? They compose of molecules, yes? And molecules are the physical objects. They are small, but yet they still physical objects. So they have to obey physical laws, and they have physical characteristics, properties. So among the properties of the atmosphere, because it composed of the physical objects, we distinguish the following one. The most important, the main, is the density, the pressure, temperature, and humidity. So now let's speak about these properties of the atmosphere and how they are interconnected. It's important to understand the relation between these processes, which processes affect what processes and why. So let's start with the density. The electrical charge. It is also a property. I mean, it's a physical phenomena, but it caused by the friction, basically by the friction between the molecules. So it's we may say secondary property. The electrical charge is not directly participating in weather phenomena that we are describing. It's like a sequence. Okay, Jeremy. So density, no problem. Density can be defined as the mass per unit of volume. Normally, like those CI units, international standard units, are operating with the parameters of kilograms per cubic meter. So this is the density, basically the amount of molecules per unit of volume. So here is the visual depiction of how density looks from low to high. Let's say you have 1 cubic meter which can be represented by the parcel of the air, or like not of the air, okay, 1 cubic meter of space, some box. And those green circles are molecules of the air. So you stuff this box with the molecules. The more you put into it, the higher the density. It can be said that the density is increasing. So, but I think the picture is pretty self-explanatory, isn't it? So this density varies with, as we said, temperature, yeah, pressure, and the humidity. Yeah, so because everything is interconnected. So let's see how it goes. Let's start with the temperature. So if the temperature increases, density is tend to. If the temperature increases, yeah, did I say increases? Yeah, increases, the density decreases. The good example is this liquid thermometer, which can be work on hydrargyrum or alcohol. So your basically your content of the thermometer is like this cube of the cubic container that we were speaking just now when I showed you this picture with those parcels, yeah, stuffed with the molecules of air. It contains certain amount of molecules. However, if you will start heating it up, it will start expanding, but the amount of the molecules is still the same. Yeah. So expansion means what? Increase in volume. So volume increases, the amount of particles remains the same. According to the previous definition, the density decreases. Yeah. Per certain amount of area, you have less molecules. Density decreases. So when temperature rises, density drops. Clear? If something is not clear, just write me, okay, in the comment section. Then, good. Then, density and the pressure. So when pressure increases, the density also increases. So here is the animation regarding that. Here in this particular example, we increase in the pressure by contracting the space, pushing the lead down. The pressure rises because how this pressure is created in the first place. Yeah, this pressure is certain force. Yeah, is the force exposed per square meter of the area. So this force is where this force is originating. Molecules of the air, as any other fluid, they are in a constant movement. So we have some problem with the internet. The video is slowly loading, but so those molecules they have certain movement, yeah. And when they collide with the ceiling of the container, with the walls of the container, they expose some force. So this force transferred per area of the container where they collide produce the pressure. So if density increases, pressure increases as well, because you leave less space for those molecules. Now should be Jana. Now should be. Duncan, it's we will get to it. Okay, we will get to it for sure. That's the good question. So you leave technically less space for molecules. They collide with ceilings of the container in this example more often, thus producing more, exerting more force. So your pressure increases. Plus, you decrease the area. Yeah. So even though the force is the same, you're reducing the area, so the pressure is rising. Clear? Next one. That density and pressure, density and humidity. So when humidity increases, the density actually decreases. We are now speaking about the density of the air. Why does it happen? Because we have, like, if to go deep inside the physics, we have something which is Avogadro's law, which says that equal volume of gases at the same temperature and pressure contain the same number of molecules, regardless of the chemical nature and physical properties. But more simply speaking, the molecule of the dry air, actually the molecule of the dry air weighs more, it has more molar mass than the molecule of the water. So when basically you have some, again, you have some parcel of air, and if you will substitute molecules of the dry air, which has higher molar mass, with the molecules of water, which has lower molar mass, you will reduce the weight. You will reduce the weight. And since the density is defined as kilograms, which is, correctly speaking, it's not the weight, it's mass, okay? Yeah, if to be super precise, it's mass. Weight is force. Mass is the quantity of the matter. So we are speaking about the mass. So you will stuff this parcel with a lighter molecules. You will decrease the mass. Mass is kilograms per cubic meter. Yeah, so you decrease the density by the physical definition now. Clear? Because density is the kilogram per cubic meter. So less kilograms, less density. Good? Next one. Pressure. What is this? Pressure is the force which is applied per certain unit of the area. You should remember this from the principles of flight. Yeah? So this is the force applied per unit of area. Force is measured in newtons. Area in meter cubic. And this force, newtons per meter cubic, is the pressure, which is pascals. When we are speaking about atmosphere, this force is where this force is originating from. We have mass of the column of air, mass of the atmosphere. This atmosphere is, wait a second. So we have the atmosphere. Atmosphere is composed from the gases. Gases composed of molecules. Molecules are physical objects. Physical objects have mass. So when you subject this mass per acceleration to acceleration, and the acceleration is what? Is our gravity. So you take the mass, you subject it to gravity, and you receive your force. And then this force, when subjected per unit of the area, gives you the pressure. So atmospheric pressure is simply the force that the atmosphere exerts by its weight. Yeah, the force is weight. So the force that atmosphere exerts per, let's say, certain area of the land. Okay, this is EASA variant. This is EASA option. Now let's. I know we have guys from the from the America. So in case of America, that would be PSI. Yeah, you measure the pressure in the pounds of force, Libra pounds of force per square inch. So again, you have Libra pound, which is the characteristic of the mass. Then you have force, which is gravity. When they two combined, you have Libra pound force. Yeah, this is analog to European newtons. And then in Europe, in metric system, we define newtons per meter squared, but in US is the square inches, not meter squared, but square inches. So Libra pound force per square inch, and you get your PSI, the pressure. So now, how this pressure, correlation of the atmospheric pressure, and let's speak about the height, because technically this is what is the most important here to understand, is the correlation of the atmospheric pressure and the height. As the height increases, atmospheric pressure decreases. Why does this decreases? Because our atmosphere and all the properties that are peculiar to this atmosphere are not. Our atmosphere doesn't exist endlessly. It's somewhere it ends. So, and atmosphere is the molecules. So those molecules are spread up to a certain extent, and then nothing, and then space. So by this logic, we understand that we will get less and less amount of molecules the higher we go, because somewhere it should end up, somewhere it should end. Plus, layers, like lower layers of the atmosphere, they contain more molecules, because imagine, like, let's say the top level, like the end of the atmosphere, you have a certain amount of molecules, but there is nothing from above which pushes them down, because there are no molecules. Yeah. Then you go a bit lower, you have slightly more molecules plus. So and this slightly more amount of molecules, they are attracted to the Earth by the acceleration, by the gravitational force, plus by the force that those upper molecules exert on them. And then you go down, and the same process, but more molecules above you are pushing you down, and more and more and more and more, way up to the ground, to your observer's position, yeah, to the ground. Clear? So this is why the pressure drops with the height. Less molecules, less kilograms, less kilograms are, those kilograms are less, less amount of the kilograms, less newtons, less pressure. Clear? Cool. Speaking of the pressure, we have, this is about the international standard atmosphere, but however, the slide specifically about the international standard atmosphere, that would be later on. But we have concept of the standard pressure. Pressure is maybe different from day to day, from period of day to period of day, from location to location, but we have standard one. Yeah, like very, science likes a lot to, wait a second, David, Nahmat, if I would ask you to disconnect the camera, that would be, can you please? Because, yeah, thank you very much, sir. Science likes generalization, yeah. So we are not in. It's not practical to check at each and certain location the pressure at any day, because we will not have an agreement what is the reference datum. Yeah, we need to do calculations. We need to build scientific models. We need some datum, some uniform datum. So this is about this uniform datum. Yeah, this is average. It's like and why I'm saying that is just like this question about the water vapor or carbon dioxide content. Yeah, again, this is it. So the average mass of the column of air which is above you, and you are now currently subjected to it, is 10 tons. Yeah, so per square meter. So each square meter of our, like, your room outside, your sidewalk next to your house is subjected to 10 tons of the air column which is above. Then when these 10 tons of air are subjected to acceleration of the Earth, which is 9.82 meters per second squared, you get the force of around 100,000 newtons, or, like, if to be precise, 101,325 newtons. And then, as the result, we can say, since this force per meter per square meter, yes, Parash, you wanted to say something? Oh, sorry, man. When they are exerting, this force is exerted for, that's fine, don't worry. When this force is exerted per square meter of area, we get our pressure, which is 101,325 pascals, or because this is like this number is too big, so we use hectopascals, where hecta stands for 100. So it's basically your amount of pascals divided by 100, and as a result, you have 1,013.25 hectopascals of the pressure, which is standard pressure. For those who are flying, Parash, Anna, standard pressure 1013 hectopascals. Yeah, like the you definitely heard this. So this is the standard pressure. Standard pressure of at the Earth is 1,013.25 hectopascals, 1013.25, which is again simplified to 1013 hectopascals, 1013. Cool. Then that was Piazza variant. Now American variant. So you guys in America don't use hectopascals. You use inches, like inches of mercury. So how does those inches of mercury originate from? Initial concept is the same. So you have sealed column of air that has a footprint on 1 square inch, because in America area is measured in square inches, not meters squared, so square inch. And this column of air occupies the area from ground to from sea level to the end of the atmosphere, and it will produce 14. So the mass of this column of air will be 14.7 libra pounds. Then this column will be subjected to acceleration, and you will get what? 14.7 libra pound force per square inch. So that would be 14.7 psi, yeah, of force. But if you had any experience with aviation, you cannot, maybe you will most probably not recall this number or formulation. This is because historically the pressure was measured by the inches of mercury in the mercurial barometer. So basically, whoever is in charge of developing the standards of measurements decided, yeah, let's keep this inches of mercury, it's convenient. So we will derive standard atmospheric pressure. How? Like by measuring how much mercury will be pushed up in this I don't know, jar or whatever it is. I just forgot the right word. I mean, I know the I know what is this assembly, but so how many inches of mercury will be lifted up in this assembly when atmospheric pressure will act on the mercury in this container. And yes, cylinder, let it be. Let it be. So 29.92 inches of mercury will be lifted up by the standard pressure, by the average weight of the atmosphere, which is equal to 1013 hectopascals. So in a world, we have two systems, hectopascals and inches of mercury. But in both cases, we have something standard, and this standard is 1013 for metric system, and for US is 29.92 inches of mercury. This is the pressure. Now, correlation of the pressure and the atmosphere. So when the temperature increases, the pressure will also increase. It can be seen also here on this example. So when you increase the pressure, the temperature also increases, because again, these molecules, they collide with the walls of the container, they release the energy, and this energy is, I mean, the heat is also the form of energy, right? So you have more energy, more heat, so the temperature increases as the density, as the pressure increases. Then correlation of the temperature and height. As the height increases, the temperature, you most probably know, because many of you, or maybe all of you, were flying the airplanes, and normally pilots made announcements, like that, ladies and gentlemen, temperature, outside their temperature is minus 56 degrees. Even if you took off from Dubai and you are flying to, I don't know, some warm country. It decreases as the height increases. Why does it happen? Maybe someone can tell, by the way. Maybe someone can tell why it's happening. 3, 2, 1. Okay, it happens because of the expansion. Pressure decreases, the expansion happens of your, let's say, parcel of air, it expands. And this expansion, it takes energy for this parcel of air, it requires the energy to expand. This energy, since heat is also energy, is just transferred from one state, which is heat, to the energy that is required to push the boundaries of this air parcel. So this is why the temperature drops. This is like the sole purpose of why we have a temperature drop with altitude. I mean, now we're speaking about standard atmosphere, okay? Because we have exceptions. Sometimes it's cold at the ground, warmer on top, but that's specific cases. We're now speaking in general. So in general, this is what happens. Due to the expansion, you lose the energy, you lose the temperature. Okay, now it's time to speak about the international atmosphere here. because now we spoke about pressure, we spoke about density, we spoke about temperature. So international standard atmosphere defines the following values for the items discussed. The temperature standard is 15 degrees and drops on average of 1.98, which is again simplified to 2 degrees per 1,000 feet. Why 15? Why exactly 15? And why all the rest? Why all the rest parameters are like they are? So this international standard atmosphere was, if I'm not mistaken, was like it's 70 years of observations around the world, and the data was recorded from different locations through different time. Then there was like average numerical value for each of the parameter, and so here you have. Due to expansion of molecules from ground up, the heat decreases with pressure. Due to expansion, sorry guys, I'm reading the comment. Due to expansion of molecules from ground up. Can you reword the question, because due to okay, so the pressure drops because less and less molecules are around and above. The air parcel feels like more free. Yeah, this is the concept. Yeah. Yeah, I understand the previous slide. Yeah, so you have less pressure above. You have expansion because let's say your air parcel was on the ground, and the pressure at the ground is, for example, this 1013 hectopascals, and you create the pressure of 1013 hectopascals inside this parcel. Then you lift this parcel up. The surrounding pressure is lower. Now the pressure within the parcel is higher. So the parcel will try to, because everything goes from the area of high pressure to the area of the low pressure. So the parcel will try to expand itself. This expansion will require the energy, because even though it wants to extend, but still it has to push its limits, its walls. So this energy will be the energy required for this expansion will take part of internal energy of your parcel, which will be followed by the temperature loss. Plus, you will have less collisions of the molecule per unit of the area. Yeah, so again, less heat. So we can from different approaches. Okay, so many comments. So temperature increases with higher pressure, but density. Temperature increases. Okay, guys, step by step. Okay, what is the use more? It's different countries, EASA and the European continent, and apparently Asia use hectopascals. Inches are used in America. As far as I know, now they are used in America only. Yes, the Pascal's QNH, step by step. QNH is pressure above mid-sea level, step by step. Understood, sir? Okay. So, temperature decreases with higher temperature, increases with higher pressure. It's the physics concept. Okay, step by step. Yeah. If only I could transfer all the information at 1 second by one click, then this lesson would not be 3 hours long. Okay, let's continue. So 70 years of observations, we derived the standard data. Temperature 15 degrees and drops at average at 2 degrees per 1,000 feet. Density 1.225 kilogram per meter cubic, yeah. And pressure 1013 hectopascals and drops on average of 1 hectopascal per every 27 feet. And all of this data are at mean sea level. Mean sea level, it's again another unification of the model of the atmosphere. UNH, yes, this is the pressure at the mean sea level. However, it will be very soon. It will be very soon. Yeah, at mean sea level. Guys, this is important. Our values are all at the mean sea level. We cannot say that standard atmosphere is if we measure it at like next to our home, let's say, and our home has certain elevation above the mean sea level. No, it's at the mean sea level. And further on in ATPL, all the questions that will require calculation of the temperature, you will use the logic that 15 degrees is at the mean sea level if the question asks you to calculate according to international standard atmosphere. The sea level is the level, it's the Baltic Sea, if I'm not mistaken. Yeah, but it's the level of the sea is pretty much identical worldwide. So this is why it's taken as the average, because it's some uniform reference. Now, about the American guys, you have 95 Fahrenheit. The temperature is 59 Fahrenheit and drops on average at 3.7 Fahrenheit per 1,000 feet. The density is, I'm not sure that PPL questions asks about density at all, but 0.076 Libra pounds per cubic feet. And pressure 29.92 inches of mercury, and drops at 1 inch of mercury per every 924 feet, almost 1,000 feet. So again, as a simplification, 1 inch of mercury per 1,000 feet, reduction in pressure with height. And again, at mean sea level, of course, every time, everywhere. Cool. Guys, let's open the worksheet from today's class. All of us are having the link. Tell me if not. Make sure that you are logged in to LMS. Okay, I'll send the link. So that's the link, and let's proceed with the first task, which is general. You're welcome.
Number two.
Minus.
Sorry, three. Number three.
guys, you can do it from your computer, and let's give some time to other students here to finish these questions, and then we will go together. Okay.
Was this emailed to us?
One more time, please.
I was asking if this attachment was emailed to us. The worksheet.
The link for worksheet, it's here. Leonidas, check if you are logged in LMS. Maybe that may be a case.
Yeah, that might be it. I'm on my phone right now. Sorry about that.
Mhm. Yeah. Okay, I'll. Mm, how many questions do we have here? 4 questions, guys. Put the plus when you're done, or actually, no, I can check your results here, anyway. But let's say like this. Let's 2 more minutes, and Jeremy, yes, yes. 2 more minutes, and we will go through them, quickly explain why specifically these answers, and then we go forward about Leonidas. We'll take care of that. I hope that will not be an issue on the next class. Or after the break, maybe in something around 15 minutes, if we still have the IT department, then I'll ask regarding it. Okay. You are. Yeah. I know. It's otherwise, yeah. We are given the hint for other. But I mean, Jeremy, everyone was listening. Everyone knows that it's -5, right? Oh, again, I said, okay. Disregard. First answer is -5. Yeah, you get me. The formula that Andrei Balach. Sorry if I'm not pronouncing correctly the name or the surname. Yes, the formula that Mr. Andrei provided us into the comment section is 100% correctly. So 2 minutes expired. Let's go. What do we have? Temperature at 10,000 feet in standard atmosphere. So standard atmosphere, 2 degrees per 1,000 feet. We have 10 of those thousands. So 20,000. 20 degrees of reduction, and initial temperature, like at the sea level, is 15. So 15 plus 15 minus 20 gives us -5, and of course it's correct. Then, which of these following gases are most important? Is most important because there's only one. In terms of the weather formation, like a simplified wording, but yes. So everyone, water vapor, yeah? Yeah. Now, the relation between pressure and the temperature. What do we have here? We can send 1, 2, 3, like in comment, if you wish. 4. Pressure increases if temperature increases. That's it. That's it. Ah, yeah, there was only 3 questions. Okay, now guys, altimetry. Now you decide whether we do 10-minute break or 5 or whatever you want, or we go through altimetry and then we do the break. Because I'm fine. It's about you. Okay, let's continue. So the first was that will be attendance. Yeah, attendance would be later on, unexpectedly. Altimetry then break. That's cool. So altimeter. an instrument that, as the slide suggests, measures the pressure, and this changes of the pressure cause its needle to move. Yeah, basically, I don't know, like for when I was a kid, my grandmother had this barometer, at home, which was showing like the pressure, and then there was some encryptions, like there will be 2 degrees per 1,000 feet. Yeah, 2 degrees of Celsius per 1,000 feet. And there was some inscriptions like because it was coupled with humidity, so this Wunder machine somehow calculated whether it would be rain or thunderstorm or whatsoever. So maybe some of you had, or your grandparents' parents had. So this is like, essentially, altimeter is nothing else than aneroid barometer, where you have, remember, instrumentation, airframes, you have buffers, there's some pressure in it, and changes of surrounding pressure give you the readout. So basically, you should have general understanding of how the altimeter works. Here we are speaking about the altimeter as from the perspective of readings, because these readings are affected by the weather phenomena that are of our concern. So this is an aneroid barometer, but instead of showing you amount of the hectopascals or inches of mercury, it shows you the altitude. It converts this to the altitude readout rather than units of pressure. So what do we have here in this altimeter? In this altimeter, we do have the instrument itself, and then something which is called Colsman window. So this Colsman window is the window where you basically set the reference for the altimeter, from which pressure datum you want this altimeter to show you the height. From where? So you have this barometric adjustment knob, you rotate it, you select your reference, and regarding of what reference was set, then according to the changes of the surrounding pressure, the altimeter shows you the height, altitude, flight level readout. We'll speak about it now, how they are in, like, what stands for what, yeah. So this Colsman window, and here you have, let's say, pressure at the aerodrome level is 1018 hectopascals. Now, and imagine that this aerodrome, purely theoretically, this aerodrome is located at the sea level, and you have and now we have, actually sea level is irrelevant. No, not necessarily sea level, but standard atmosphere properties are present. So our pressure drops at the rate of 1 hectopascal per every 27 feet. So here you have this amount of feet. Yeah, 0, 27, 54, 81, and up to 270 feet. And here you have on the left the correspondent change of the difference in hectopascals. Yeah, because 1 hectopascal per 27 feet, so per 54 feet that would be 2 hectopascals, etc., etc. Now altimeter senses the changes in hectopascals. Yeah, because those aneroid buffers, yeah, they react on the change of the pressure, ambient pressure, surrounding pressure. But again, instead of showing you what is your current pressure, however it's possible, yeah, like if it was constructed as this barometer, then it would just show you the decrease in pressure. But this altimeter, the scale is calibrated not in hectopascals or whatsoever, but in feet. But since we know the ratio between feet and hectopascal, we can display these changes in hectopascal in feet. So this is what this altimeter gives you. So it senses the change of 10 hectopascals of pressure in respect to the datum, and it gives you the readout of 270 feet here. So your airplane will climb, and your needle will move correspondingly. Clear? Cool. The United States, guys, same logic. Physical process is the same, but we remember 1 inch of mercury per 1,000 feet of altitude. Yeah. Let's say here the pressure difference is 0.3 inches of mercury. Yeah, 0.3 inches of mercury. So it shows you 300 feet. Yeah, in standard atmosphere. The logic is the same. And again, you have Colesman window, you select your reference line, and here you go. Now, as pilots, the thing is, we are not always interested in showing us the vertical distance from the aerodrome. So here is about the questions. That is this easier. The American option is also not very complicated. What I wanted to say, yeah, this is about the question that we had before in class about QNH and other Q codes which are relevant to altimetry. So we are not always interested in showing us the vertical distance from the ground. What is the solution? Select another reference. This is the solution. So if we are speaking about the pressure at the aerodrome elevation, as it was previously shown on the picture, then we refer this to the QFE, and the readout of the altimeter would be height. So if you select a reference of the altimeter as pressure at your aerodrome level, the altimeter will show you the height. If you will select the pressure datum reference at the sea level, that would stand, the Q code for this would be QNH, and the altimeter will show you the altitude. If you will select the standard pressure, 1013 hectopascal, the altimeter will show you the pressure altitude. The Q code for this will be QNE, and sometimes this pressure altitude is also called as the flight level. Okay, so if we have 1018 at airfield, but I don't calibrate, I will get minus VE altitude reading. What does minus VE stands for? Yeah, guys, I lost the thread. So negative about what? So if I have 1018 at the airfield, but I don't calibrate. No, like, okay, you have 1018 at airfield and you don't calibrate. And sorry, I didn't get the question. Like, I get a minus VE altitude reading. Okay, step by step. Now we will see how does it work. So pressure, altitude. Again, Q codes, QFE. Now it will be clearer. So QFE, height, QNH, altitude, QNE, flight level or pressure altitude. Something like those names are interchangeable. Can be flight level, can be pressure altitude. Okay, so this is how this graphically works. So let's say you have the airfield. The airfield is located at certain location. you measure the pressure at this airfield location, and from here you will have your height, AGL, above aerodrome level, yeah, in this case, AAL, above aerodrome level, altimeter will give you the height. But this is not really cool, you know, because different airports, like even if they are spaced relatively close together, they still may have different pressure between each other, and like there will be no uniformity, you know, like it doesn't make sense to select altimeter according to the pressure at specifically this airport, because that would be applicable only to this airport. Like you go to another airport and it doesn't work anymore. It's, for example, Parash, yesterday you were flying, QNH of Letnyany and Gbely was 1019 and of Praga 1020, or vice versa, I don't remember. But anyway, I mean, pretty closely located airports, but still different pressure. So it doesn't make sense to do this as the reference. It's far more convenient to make QNH as the reference. QNH also changes with lateral distance, but not that fast as QNE, because as QFE, sorry, because sea level is uniform more or less. So it changes. It depends on the pressure systems about the areas. Now we're speaking about quite extensive areas. Yeah, like for example, QNH of western part of Prague, QNH of eastern part of Prague. Yeah, it changes, but not that fast as QFE, because QFE will depend not only on lateral changes, but also on elevation, on what surrounding environment of this airport is like, but mostly on elevation, of course. So QNH is far more convenient to use, because look here, here you see the QNH and there's the airfield elevation, something which is called airfield elevation. So this is airfield elevation is the elevation of the terrain above mean sea level according to the normal pressure gradient. Yeah, so let's say you have QNH, you have you know your elevation from the sea level, so you can it's actually, sorry, it actually works, don't get confused. I deviated quite a bit, but I don't want to confuse you. Let's unwind back, because if we will have this topic deviations, we will get confused. So again, QNH is far more convenient because it not changes as fast as the QFE. However, QNH still changes laterally, not fast, but changes. And if we are flying some Cessna, it's fine for us. We can fly on QNH, no problem. But if you have an airplane which is faster, then you are not actually interested in flying on QNH, because it will still change. It will reduce your workload. From time to time, you will have to reset the altimeter. For what? It's far more convenient to fly at standard pressure, which is 1013 hectopascals. Now again, don't get confused. QNH is the pressure at sea level, and in standard atmosphere, the pressure at sea level is 1013 hectopascals. But it's when standard atmosphere conditions are prevail, which is quite rare. So normally QNH is different from 1013, but 1013 hectopascal pressure level is still exists somewhere. Not necessarily at the sea level. It can be above sea level. It can be below sea level, but it exists. So you can choose this as reference, and this is what high performance airplanes normally do when they fly high. They select standard pressure as the reference, yeah, and they just follow this line of the standard pressure, 1013 hectopascals. Yeah, their true altitude in respect to the ground changes with this changes of the location of this isobar. This line is called isobar. The line joins equal the areas of the equal pressure. The true height is changes, but we don't care because we quiet height, we are above any elevations of terrain whatsoever that can affect, and we're more interested in maintaining vertical separation in between each other. So if everyone flies at 1013 hectopascals, then everyone has the same understanding of the of their like relative position in between each other. QNH is used in a lower altitude band because QNH is mainly used to get clearance from the obstacles and elevation of the terrain. Because all the known elevation of the terrain, let's say I'm now, what is the elevation? Elevation is the vertical distance from the sea level to the point of the observer. So my airport is located at certain elevation. At certain elevation. So this elevation is mentioned on the chart, mentioned on ICAO chart, on aerodrome chart, in AIP, whatever. It's known and it's mentioned. So for me, it's more important to get clear of the terrain in low altitude band and still having the separation in between each other, between the airplanes, because in low altitude band, all the airplanes are flying according to the QNH, and everyone also have the same reference for the altimeter. Then we go higher, we don't care about the terrain anymore, we can select 1013, the pressure, the standard pressure, and we will not change it through the lateral distance, because QNH we had to change. We would have to change. The altitude at which changing from QNH to QNE to Q standard pressure happens is called the transition altitude. And where the change from standard pressure setting to QNH happens is called the transition level. Let me check, do we have this slide? No, I don't. So wait, I will open the, strange that this slide got lost.
Hi, could you please repeat again transition altitude and transition level? What's the difference?
That's exactly what I was about to draw now. I understand that on words is wait, I'll draw now. So we have sea level. We have some, I don't know, mountain here, whatever. So in the altitude band, normally how this transition levels and altitudes are defined. In the altitude band up to wait a second, just a second, I need to. Welcome, Nikita. Okay, so in the vertical range, normally up to highest elevation of the obstacles in the region, we have area where we fly on the QNH. So here we would fly on the QNH. Outside of this region, we will fly on the QNE, on the standard pressure setting. So in this altitude, in this band of vertical distance, we will call our vertical distance as altitude. If we fly under the QNH setting, we will call our vertical distance as flight level. Flight level. Now there is naturally there will be some boundary where we change from one to another. So where we change from the QNH to the QNE, that would be transition altitude. So the physical boundary, let's say, established vertical distance, yeah, where we change from QNH to QNE would be transition altitude. So easy to remember by writing the name. So transition altitude, and where A can be drawn as the arrow up. So when you go up from the QNH to QNE, you draw altitude. And on the way back, when you descend, you have transition level. Yeah. And also it can be understood because in this region you fly at, like, your vertical distance is referred to be altitude. So of course that would be transition altitude, where you change to the standard pressure setting. And here on the way back, you are flying under flight level, so you'll have changed to the altitude. So that would be level where you change, transition level. And in between them, you have transition layer. This is the layer, this is rather from operational procedures, this is the layer where these transitions are happening, yeah, where you can, the designated vertical distance where resetting of the altimeter can happen. Okay. So again, QNH is the pressure at the sea level, and when we fly according to the pressure at the sea level, it's, like every country has its own designated list of transition altitudes and levels. So for example, transition altitude in Czech Republic is 5,000 feet. So after 5,000 feet, if you climb higher than 5,000 feet, you have to change the reference of the altimeter from the QNH to the QNE. So whatever, so the vertical, your vertical distance starting from 5,000 feet would be referred as the flight levels. Not on the map. It's in AIP. So it's in AIP. You go to general rules and procedures, and visual flight rules, and it should be somewhere here. Wait. Or no, there should be altimeter setting procedure, specific, sorry, here, in route 1.7, altimeter setting procedure. So transition altitude. So this is in your IU, yeah. Transition altitude is the altitude at or below which the vertical position of the aircraft is controlled by the reference to the altitudes, except as stated in a certain paragraph. The transition altitude within all flight information region of the Czech Republic is 5,000 feet, MSL. And then transition levels, they are actually changing. There is even a table depending on which QNH, which transition level would be in use. So it can be the lowest one can be 5,000. 50, correct, say, if the QNH is within this range from 1014 to 1050 hectopascals, that would be 60, and so on. But for now, that's enough. Okay? Clear? Now, the thing is with the altimeters that they are all calibrated to the ICAO standard atmosphere. All altimeters are utilizing the logic that 1 hectopascal of change would be depicted on the altimeter, indicated on the altimeter as 27 feet of the altitude. And 10 hectopascals would be indicated as 270 feet. All the time, all altimeters are working in that manner. However, it doesn't happen in reality often. It doesn't happen in reality. But altimeters, they don't know about this. So, okay, two questions. How does this affect us, and why it's happening like this? So why it's happening, let's start with the second question. Why it is like that? Why all altimeters are calibrated to the standard atmosphere? Well, because basically we need some uniformity. The altimeter should be working according to some standard pattern. Otherwise, it like best case scenario, you will have to manually readjust this altimeter using some tables, and it will increase the mistake. After all, we really don't care about those mistakes much. There is exceptions. In some cases we clear very much, we care very much, but generally we don't, because when the airplane is airborne, we more interested in maintaining separation between other airplanes. And if all the airplanes around you would have the same altimeters, yeah, they all would be subjected to the error with the same magnitude. Yeah, or the same magnitude of the error would be for everyone. So yeah, if your altimeter shows you less altitude than you actually are, so does the altimeter of your airplane which is next to you would also show less. So still the indication would be the same. We do care about this in the proximity to the ground and in the proximity of the obstacles. However, step by step. Where this problem is originating from. We said that altimeter is calibrated to show you change 1 hectopascal of pressure. It gives you the reading of 27 feet of change of altitude. Now let's, for a second, let's put aside the hectopascals. Simple example. You have 3 columns of air. One is the standard one, another is the colder and warmer. So both of them contain the same amount of the molecules, and consequently, they all exert the same pressure at the bottom. Each column exerts the pressure at the bottom of 10 units. Yeah, not hectopascals, inches of mercury, just 10 units of pressure at the bottom in each case. So then we said that the cold air, the hot air expands while the cold air contracts. Consequently, in the warmer the column of air that is warm would have greater vertical extent. But at the same time, all of those 3 columns would have 0 on top. Yeah, so all of them are having 10 at the bottom and 0 on top. As the result, what is the consequence out of this? We will have different lapse rate. The pressure lapse rate would be different. So you see here in cold air is like 10, 9, 7, 6, very fast. And in warm air is gradual reduction in pressure because the column is expanded. Yeah, so 0 at higher height in respect to the ground. And our altimeter will let's say 1 unit is 100 feet. So our altimeter will give you what is the change here of the units? Is 10, is 0, 1, 2, 3, 4. So 400 feet. 400 feet, altimeter will show you because it senses the pressure which corresponds to 6 units. But in areas of the different temperature properties, you see that the true height, the true vertical distance between reference and your position, between like bottom of this diagram of your position, would be different. So in warm air, the altimeter would think it's higher than it actually is. Exactly. In warm air, the altimeter, wait, what did I say? In warm air, no, in warm air, the altimeter would think lower than it actually is. Sorry. Here, the middle column is your standard atmosphere. Yes, middle column is your standard atmosphere. Here, altimeter reads the pressure difference of 1, 2, 3, 4 units. We agreed that each unit stands for 100 feet. So 400 feet of height of vertical distance, altimeter shows you here. In this warm column, altimeter also shows you 400 feet. However, we see that we are physically located higher. No, no. Pressure is like the force exerted by those molecules. It's not about sensing the quantity of molecules, but what pressure this molecules exert on you. Yeah, so again, 10 at the bottom, 0 at the top in all 3 columns. But look at the rate. Yeah, they all have 10 at the bottom. Yeah, don't look at the physically the digit that's smaller. It's 10 at the bottom everywhere. But it's, for example, where it's 9 in warm air column, it's 8 in standard, and it's 6 in cold. Yeah, so different rate. So again, in warm air, altimeter will show you lower height than your lower vertical distance than you actually are. This is why we have indicated in the true altitude. And so this is how it works. Here in this example, all the altimeters that shows the isobar. Yes. Yeah, this is isobar, and here is also isobar. Yeah, because isobar is the line of the equal pressure. So 6 column here, 6 column here, 6 units here, 6 units here, 6 units here. Yeah. So this is isobar, same pressure, and here is the same. Yeah, just more like different picture, more advanced picture. So you have. In each cases, the altimeter shows you the 10,000 feet, for example. But in warm air, since the column is expanded and thus the level where the pressure, which is peculiar for the standard atmosphere, is located at the higher height, your true altitude would be more. And in colder is vice versa. Here, again, this is the isobar. Yeah, the line joins equal pressures. In warm air at certain height, you will have higher pressure than in colder air because of this picture. Always imagine this column of air which has 10 at the bottom and 0 at the top. Warm air column is bigger, so it will have for certain vertical distance, for certain height, it will have higher pressure than the column of the cold air. Okay, write me if it's clear, because it's here, it's just like in front of you of the picture. Yeah, take the upper portion of the column. Here is 1. Do you see the mouse pointer? Yeah, here is 1, but here is already 0, and here is already 0 for a long time. Or here is 9, here is 8, here is 6 in the cold air column. Yeah, makes sense? For the same height, for the same vertical distance, you have higher pressure in the warm column of air. Okay, thank you. Anyone else? For anyone else is clear? Okay. So yeah. So that's the difference between. So this is the altimeter error. Yeah, that in warm air the altimeter shows you your true altitude is higher than your indicated altitude, because altimeter doesn't have any idea about the temperature of this column. He just knows, he just feels the pressure, and this is it. He feels the pressure and shows you correspondent will think. So again, so at the same level, for warm air, the altimeter will think it's a lot lower altitude. At the same level, for warm air, altimeter will think it's yes. Yeah, roughly, yeah. Because the pressure increases the lower we go. Yeah. So if you had 10 at the bottom, 0 at the top, and you expanded it, so yeah, it will think that, yeah. Okay, so let's go to this altimetry, the classwork part 2. Is this the reason why in denser, colder air it is easier to take off and land smoothly than in higher temperatures? This is the density altitude. Yeah, actually, density decreases as temperature increases, and yes, so I mean it's not directly the reason, but the temperature is the guilty one here. So in cold, yeah, yes, Jeremy, yeah, the cold air is more dense. So per each bite of your propeller, let's say there are more molecules propelled, yeah, and the performance is consequently better. Okay, so let's open the second task, and there are like 4 questions. So I'll give you 5 minutes. We'll go through them and we'll make a break. Just type in the plus when you will finish, okay? Thank you. Okay, one more minute and we'll go through the... Okay, let's go. So referring to the picture, the altitude indicated on the altimeter of the airplane. So what is the correct answer here? 2 is the same. Yes, because altimeter has no idea about this expansion, contraction. Yeah, it follows this line of the equal pressure and doesn't care. Okay. If it's necessary to reset altimeter from 1013 to from 1003 to 1013, what's gonna happen? Anyone? Okay, 1. Altimeter will indicate approximately 300 feet increase. Yes, correctly. Do you guys, did everyone understand why it's happening? Because 1013 hectopascal pressure setting is located lower than 1003. Yeah? Because the temperature goes up, the lower we go. And since we resetted it to the lower reference, it now calculates shows the height from the lower reference, so meaning that we are higher. If someone doesn't understand, don't hesitate. I will draw the sketch. We'll find a solution. Okay, what about here? Two. So okay, Letnyany QNH 1002, the elevation 900. What is the QFE? So it should be lower. Should be lower. Yeah, of course. QNH. Actually, yeah, this is how the QNH, by the way, is. This is how QNH is calculated. QNH is calculated from the QFE. Yeah, we measure the QFE. So let's say we establish the airport, we come with the altimeter, measure the pressure at the aerodrome. This is the pressure, the QFE. And then by applying the logic of standard atmosphere, we calculate the QNH out of it. Even though the lapse rate may be different. This is for ATPL, but actually QNH is pressure that would be at the mean sea level if standard atmosphere would prevail. But I just don't want to confuse you guys too much. Because if you want to calculate according to the present lapse rate, there is another thing. But there's another procedure. And that pressure is called QFF. But I mean, I will give you the slide, because if for altimetry, even on ATPL, there is a whole separate day dedicated to altimetry. I'll give you the slide. You guys at home, please go through it and try to. I'll just show you what information you have to study. So one vertical distance, so altitude, yeah, from the mean sea level for sure. Now I'll give you the slide. It's from ATPL class. Take the picture. This picture. This is the QNH and the QFF. Write at home. Read at home what those are standing for. Make a screenshot. Take the picture. And also altitude correction for the non-standard temperature. Temperature correction. And next slide. Okay, guys, let's go for the break. No. Attendance. So I'm opening the attendance. Wait. One second. Okay, it's loading. Apparently, it will be open now. Yeah. Yeah, just a second. This one, yeah? Done? Done. You're welcome. Okay, we have kind of slow internet. The attendance was almost open. Okay, after the break then, because it takes some time. Okay, no, wait. Yes. So you have 15 minutes to press attendance button in your worksheet. I'll be in 12 minutes, okay? So see you. Okay, guys, I'm here. I'm back, and I see there are dozens of comments which are timeout, timeout. Same here, same here. Try to reload. Nothing had changed. Okay, I'll open another attendance in some 15 minutes. Okay. Okay. We'll reset. Okay. So let's continue. Weather, finally. Almost there. Almost weather, but still there will be one deviation more. How can we define the weather? Here, the weather is the state of the atmosphere. More specifically, the behavior of the air. Okay, guys. What's the time? Am I not early? Yeah, so fine. The state of the atmosphere, the behavior of the atmosphere, and how we can describe this behavior. What is the behavioral setting of our atmosphere? Well, the most important is that it's in a constant movement. So it not just resides at certain location. It's all the time. It's moving somewhere, and where it moves. Let's figure out. I think the best illustration of what's happening in our atmosphere is the lava lamp. Lava lamp, because let's look at the lava lamp. We will not look 5 minutes for the lava lamp, but what do we have here except for the advertisement of Koshek CZ? We see the lava lamp where some paraffin substance goes up and then goes down and then goes up and then goes down. And why it's happening? Yeah, this is something related to the temperature. And the density. Let's figure out what exactly. Deeper investigation of what's happening. Lava lamp. In our atmosphere, as in lava lamp, hot matter rises, cold air goes down. So what goes up must go down eventually, and our universe doesn't allow us to create a vacuum. Yeah. So the nature fills up the emptiness. So these three fundamental parameters are in charge of the atmospheric processes that are happening on our Earth. Hot matter rises, what goes up must go down, and nature fills up emptiness. Why does hot matter rise? So the hot matter rises because when you hit the parcel of air, so let's say this container, I didn't find better animation than this container, but let's say this is parcel of air. When you heat it up, it expands because the heat is the energy, the molecules receive more energy, they start more actively moving, colliding against the walls of the container, thus expanding it. And when you cool down the air, it shrinks, you decelerate the molecules, so they are not expanding the boundaries of the parcel of air that much anymore. So yeah, we have heating and expansion. So when this expansion happens, volume increases. When volume increases, density decreases. And as the result, since the density decreases, the less dense air floats above more dense, colder air, just like less dense objects are floating on top of the more dense objects. For example, as this piece of wood is floating on the water. Yeah, why this wood doesn't want to sink? Because it has less density. So the same here, but this density decrease is caused by the heating, expansion, and losing of the density. Clear here? Now, how exactly does the air heat up? So in lava lamp, it's kind of clear. Yeah, it's heated from beneath by this heater element at the bottom of the lamp. But what about the Earth? The sun is on top, not below. Here's the thing: these sun rays are transparent for the air. I mean, air that does not absorb them, and they. If you would think that not exactly reflection, it's just different form in different band, in different wave band, the radiation of the different nature. I mean, guys, it's important to understand that the atmosphere is heated from beneath, as in lava lamp, not from above, not by the sun. If the sun would hit the atmosphere, first of all, we would have, the higher we go, the hotter the air would be. But even a part of it, more importantly, we would not see the sun. Because if the sun would be, if the energy, this electromagnetic energy, which is also the light, would be absorbed by the air, we would not see the sun because it would be absorbed. So it's not. The air is kind of transparent for the sunlight. But however, even though the air doesn't want this absorption, the ground absorbs willingly this sun, and then it re-radiates. Exactly, Jeremy. Radiation from the Earth's surface, which is hotter than the air. Exactly, the ground re-radiates this received energy to the air. So the ground hits the air, and as a result, we have basically the same as in lava lamp. Yeah, in lava lamp, the heater, there you have this coil beneath, and in atmosphere, you have the heater beneath, which is the Earth. Good. The ground in this case is like a translator for the air. It translates the energy to the language which air can understand and pick up. So the air can pick up heat from the ground, but not from the sun. Okay. Reflection is a bit different. When you have reflection, you don't have heating at all. For example, why it's, I mean, there are more reasons why, but for example, in winter, it can be sunny day, but you will not have any increase in temperature. I mean, slightly you will have, but this is rather due to concrete buildings. When you have reflection, the energy goes away, goes back to the space where it came from. So again, the movement of the air, the atmosphere is in constant movement. Weather is this phenomena associated with movement, and this movement is caused by one and single reason. This is the heating of the Earth's surface by the sun. And since now we know that the heating element of our planet is located beneath, on the ground, we can speak about the vertical structure of the atmosphere. Wait. The vertical structure of the atmosphere. I just wanted to reopen the attendance. Let's try. Or it may be in half an hour. Okay, let's do it at the end of the class. Yeah, of course, I'll go back now. Where exactly, John? So the vertical structure of the atmosphere. The atmosphere is divided into 5 concentric layers, which are troposphere. This is where we exist, and most of the flights are conducted. The stratosphere, the mesosphere, and the thermosphere, and something else, exosphere. As I said, all of the things that are in scope of this subject are happening in troposphere or stratosphere, mostly in troposphere. So let's see, division of this is based on the vertical profile of every temperature changes, chemical content, and density, but mostly temperature changes. Each of the layers is divided by such so-called pause. So maybe you heard something like tropopause. So this is the layer which separates troposphere from stratosphere. Then you will have stratopause, mesopause, thermopause. That would be the divisions, layers separating one layer from another, one segment of the atmosphere from another. So as I said, we are mostly concentrated in the troposphere, around the troposphere, yeah, because commercial jets, like I'm not speaking about Cessna now, they're definitely were flying in troposphere. This is the lowest layer. Even most of the commercial jets are flying in the troposphere still. Maybe some of them are in tropopause. Some of them are higher than tropopause, but that depends on the season and location. There will be a slide about it. So the temperature, what do we know? What do we need to know about the troposphere? This is the segment of the atmosphere where the temperature drops at 2 degrees per 1,000 feet, down to minus 55.6 degrees at the tropopause. So at the tropopause, in standard atmosphere, at the tropopause at minus 56.5 degrees, again, in standard atmosphere, it can be different, but the reduction in the temperature stops and the temperature becomes stable with height. It's not decreasing or increasing. Then in the stratosphere, the temperature starts rising. It's rising because of the presence of the ozone layer. So from the perspective of the chemistry, what happens there is that you have oxygen, formula of the oxygen is O2. Yeah, formula of the, so two molecules of oxygen. Formula of the ozone is O3. So when the solar radiation splits the molecule of the oxygen, O2, in two, and then they regroup those molecules, atoms combine together to create O3. So this process is followed by the heat release. So this is why basically we have the increase in temperature after the tropopause. So we have drop in temperature in troposphere, tropopause, where the temperature is not changing with height, and then the stratosphere, where it's rising, then it decreasing again, then it increasing again in thermosphere, but due to some different processes which are out of scope of the PPL, even ATPL. So this is the vertical profile. The density changes. The density changes only one direction. The density changes all the way down. The pressure, sorry, pressure, and the density actually as well. The pressure changes only down because we have only less and less air above. The vertical depth of the troposphere, this band of the atmosphere where we exist, is variable. It's variable over equator, it can be up to 20 kilometers, while over the poles, it's like 6 kilometers on average. We will now speak speak about phenomena associated with this. But it's important to understand that over the equator is the highest. The troposphere has the highest extent, and over the poles the lower extent. Guys from the US, this is a slide for you. Basically, everything is the same, that just converted to the units of the US. So 3.57 degree Fahrenheit drop of the temperature per 1,000 feet in troposphere, up to minus 69.7 at the tropopause. Then the thickness of the troposphere over equator is up to 12 miles, and as low as 3.7 miles over the poles. Why it's happening like this? The hint is because uneven heating of the Earth. Yeah, because polar regions receive the least amount of the insolation, thus the temperature. So, and we know that in high temperature the air expands. So that's why. Circulation of the atmosphere. Yeah. Again, I said the atmosphere is in a constant movement. Why? Because the heating. Yeah, but now we need to add another component: differential heating, uneven heating. Yeah, it's unevenly heated by the sun, the atmosphere. So this is why we have different temperatures, thus different pressure gradients, thus movement. Because if we would have the same insolation everywhere, like pretty much everywhere would be the same temperature, and no changes in density, pressure whatsoever, only in vertical profile. But again, then it would be pretty stable, because at low altitude you have higher pressure, at higher altitude lower pressure. So differential heating, this is what causes the real movement, as in understanding that we know. The reason for that, the tilt of the Earth is the reason for that, because there are periods of there are seasons when northern hemisphere receives more insolation. There are periods when southern hemisphere receives more insolation. Yeah, this is because our Earth is tilted. Yeah, 23.5 degree in respect to the celestial axis of rotation. And it's always rotating, but it rotates. It's always tilted. It rotates around the sun, and this is why you see in autumn, in winter, sorry, the southern region, southern side of the planet is tilted to the sun more, and in summer, as we know, summer in northern hemisphere, the northern hemisphere is tilted more directly to the sun. It's not about proximity of the surface of the Earth that is tilted. It's about the angle, because let's say you have the sun beam, which is 1 square centimeter, the area of the sun beam, which has the area of 1 square centimeter, and it directly pointed to the area of 1 square centimeter. So 1 square centimeter of sun hits 1 square centimeter of Earth. 100% effectiveness. I mean, it's figure of speech, yeah. 100%, you have 1 per 1. But if I will tilt my planet, my surface, as you can see here, yeah, then my sun will be spreaded. 1 square centimeter of sun beam will be spreaded towards more surface. And so now 1 square centimeter of sun hits, let's say, 10 square centimeters of the Earth. Efficiency drops, and less insolation happens, and thus less less heat, the surface receives less heat, there's less ability to heat the atmosphere above. This is why polar regions like North Pole, South Pole, they are so cold, because doesn't matter which layout and orientation of the planet through the season, but it's almost every time there is like such a small amount of the sun that is coming there. I mean, the tilt is so big that sunbeams are spread through very huge area. However, equator is the lucky area on our planet in this term, because it always receives more or less high amount of the insolation. Plus, we have these transition periods in spring and summer, so there are 2 times when the sun directly shines on the equator without any tilt. So, as the result, no, for example. No, for guys, for PPL stage, EASA guys stick to EASA units of measurement, FAA guys stick to FAA units of measurement without interchangeable conversions. There will be none. I mean, as such questions were not reported, let's say like this, I cannot say you that there will be none forever, because God knows what's going to be added later on, yeah, to the testing system from the side of the Austro control. Of course, they are not reporting us what have we changed. Yeah, if this question appears, it may happen, but it was not reported before. But this is, it's general. It's the measurement unit conversions. Going for the meteorology subject wouldn't be extra if you would revise conversion between Fahrenheit and Celsius, just in case. Okay. So thus the equatorial region receives the more insolation through all the time. Now, what happens next? What is the consequence of it? Let's say here's the local pattern. Yeah, as in lava lamp I showed you. Yeah, hot air rises, cold air sinks, cool air replaces hot air, and this circulation happens. Yeah, because 3 lava lamp laws: hot, cold, and nature absorbs vacuum. This is the local pattern, but let's speak about something general, because since this is the whole lesson basically about general things. Yeah, so general pattern, global pattern. We have so-called circulation cells. And these circulation cells exist because of this uneven heating of the Earth. Now I will try to explain them. I'll try to explain them briefly. I really don't want to make it unnecessarily long. So as you can see here, we have some arrows. Yeah, arrows up, arrows down, arrows up, arrows down. What are those arrows? Well, basically the arrow represents you the direction of the air movement. So over equator, we have ascending pattern. Yeah, the air rises. Why? Because it's hot. Hot air rises. Yeah, lava lamp. So hot air rises. Then it reaches certain altitude. It cools down, and then it goes sideways. Why does it go sideways? Here are 2 reasons. First of all, there is a limit up till which we can, like, the air can rise. Somewhere it will stop rising, yeah, and then you cannot accumulate air endlessly aloft. Yeah, it will start spreading away. But the more importantly is that it goes this direction because of the pressure gradient. We know that the air goes from the area of hot, the air goes from the, and all the liquid fluids in universe, from the area of high pressure to the area of the low pressure. So for some reason over equator, the pressure at certain altitude is higher than at the same altitude in mid-latitude region. Why does it happen? Because of this slide. This slide, the altimetry slide. This one, yeah? Because expanded air, hotter air, has at a certain level higher pressure at the given height, it has higher pressure, yeah? So, and since everything goes from area of high pressure to the area of low pressure, naturally we would conclude that the movement, if that would be real air, then we would have the movement of the air in the direction to the left, yeah? From this area of higher pressure to the area of lower pressure. Make sense? Makes sense, yeah? Because, yeah. So, okay, what was this slide? Oh, we have full screen option. Nice to know. Now, 10 seconds, I'll take it back. Okay, so this is what. Then look at we explained the pattern over equator. Yeah, it goes sideways to the mid latitudes. Now pay attention what happens in the lower level. The air goes towards equator. Why? Because third Lavalem law says that we cannot have vacuum. Yeah, if some air was replaced, from certain location, new air has to rush in to fill up the emptiness. So this is why we have suction, basically suction of the air in the equatorial, towards the equatorial region. Yeah. So, and we explained our first circulation cell. Then let's go to the circulation cell, polar circulation cell, because Ferrel abandoned it for so far. Let's go to polar circulation cell. What happens here? Cold air tends to shrink, increase in density, and descend. So this is why we have this primary mechanism, yes, startup mechanism here. It goes down. Then, of course, it cannot accumulate endlessly next to the ground. So it will go sideways. Make sense? Makes sense. Now, here, it will warm up a bit and will start rising. And when it will start rising, where will it go? Again to the polar region, because here the air is hotter than over the pole, so the higher pressure aloft. So again, we have the pressure gradient force makes our air moves towards the polar region. Clear? Clear. Now, I mean, if not, write me down. And the last one is the Ferrel cell. Why does Ferrel cell exist? Just because two other cells exist. This is the slavery cell. It exists only because those two exist, polar cell and the Hadley cell. The cold air. You mean about this blue line? It's inaccuracy in drawing. I mean, it rises a bit. It also, there is a, if go to very details, then you have the air, hotter air brought from the mid latitudes towards more like polar latitudes, and here in contact on this conjunction, they warm each other, then they rise. I mean, this equatorial warms this color, they rise, and again, because nature fills up emptiness. Yeah, it warms up. Yeah, exactly. So, and the Ferrel cell exists just because those two exist, because it's slavery. Now, Now we will speak about the Coriolis force, because this is the global wind pattern. So now we will speak about the Coriolis force. Why the rockets are launched for the... I will disconnect and connect again. How about now? And is someone else experiencing such difficulties with hearing? Then, Rusi, it may be due to the internet connection. So, why the rockets are... Okay, that's good. Oh, thanks. Why rockets are launched from the equator? Unexpected question from my side, which I'm gonna answer myself. Okay, because the rotational velocity of the equatorial regions are simply higher. Because the Earth makes one revolution around its axis per 24 hours, right? So, and the Earth is, I mean, it's of the spherical shape, so we have definitely smaller radius, circumnavigation, smaller radius closer to the poles than over the equator, but still we need to rotate all these different distances per same unit of time. If we need to cover more distance per the same unit of time, we need to increase what? We need to increase our speed. So this is why equatorial regions are rotating faster. And this is why we launch rockets from as close to equator as possible. I mean, which is not applicable to Baikonur, I believe. They could find better location, but anyway, there was some strategic considerations for it. In general, it's like this. So Earth helps us to get speed. Now, the air in the contact with the Earth, it also rotates with the Earth. I mean, the Earth brings the air along due to friction. And because of this, the air at different latitudes have different velocity, different rotational velocity. Now what happens? Now happens this magic. We have air moving tendency from the equatorial region to the polar region, yeah, closer to the polar region, right? As we discussed just. What's gonna happen with this air when it will move towards the polar region? It will be deflected into direction of the rotation. Why it will be deflected into direction of the rotation? Because it has higher kinetic energy. Imagine you and your friends are I mean, this Coriolis force for some people it may be hard to understand, but we will try to make it. Okay, let's do this example. So you have one car. Yeah, I'm very talented artist. So this is the car. Okay, just use a bit of imagination. So this is the car which travels at 50 kilometers per hour, that direction. And now no, it's because as I explained, we have tendency at high altitudes for the air to move from equatorial to the polar regions, and now I explain why it's deflected to the direction of rotation. However, magnetic polarization of the Earth, as in gyroscopes, I do not exclude that it somehow may be related. I'm just simply saying that I never heard about this, but it doesn't mean that it's not exist. We live and learn all life, so maybe there is. I mean, I'll explain from the more simplified perspective. So we have one car. It travels 50 kilometers per hour that direction. Then I'm in my car with my friend. So in this car, there's my friend number one. Here in this car, which travels 200 kilometers per hour, me and my friend number two, we would like to drop the ball. We would like to pass the ball from this car to that car. So when we will align somehow I should have, no, I definitely don't need the ruler. Okay, so when this car will approach, and of course it will overtake it, it moves faster. So when it will be abeam the second car, and I will drop the ball from this second car to the first one. Will it hit this car? No, because the ball has kinetic energy, so it will miss. It will go there because it has initial velocity of my car. We were the same system. This ball and me in my car, we were the same system. So I drop it. It still have some leftover energy from my car, so it will not hit the car which travels at 50 kilometers per hour. It will go slightly towards the direction of the movement. So the same happens around the Earth with this global air circulation. Yeah, the air is deflected towards the direction of rotation of the Earth. When we're speaking about high altitude pattern, we will now see what happens with the low altitude pattern. Clear? Okay. That thing that I just described is responsible for the presence of the jet streams. The jet streams are normally exist at the conjunction of those circulation cells. So we have subtropical and the polar, and sometimes we have Arctic jet stream, and sometimes we have tropical equatorial jet stream, which goes opposite way, but leave it to ATPL. Okay, normally jet streams are areas, the streams of air, jet streams, which are flowing into the direction of rotation, which are happening at the conjunction of the cells because of the pressure gradients. It's about the upper pattern. What about the lower pattern? So in lower pattern, as we can see here, we have reversed thing. When we speak about the air which goes in the vicinity of the ground, these lower portions, it deflected into the opposite way. I mean, let me be clear. It's not super precise definition of where it's deflected. You can say that in northern hemisphere, it's deflected to the right into direction of the movement, and in southern hemisphere, it's deflected to the left. That would be more correct. I mean, into direction of the pressure gradient force. So here, this red arrow is my high altitude wind direction. It goes from the equator to the polar region. It's deflected to the right. In southern hemisphere, it's deflected to the left, into direction when we are speaking about the relative to the direction of the movement. Now, this green arrow is the lower current of the air. Yeah. So if we will take into consideration, for example, this Hadley cell, so you see here we have flow of air from polar region towards the equatorial. Yeah, it will be deflected also to the right, following the same logic as on this picture. Let's say now I want to drop. How did I do that last time? How is selected? Now I want to drop the ball from the car which travels at 50 km/h to the car which overtakes me at 200 km/h. So in this case, the ball, if we are dropping from 200 to 500, this is high altitude pattern in equatorial cell, it goes that way. Yeah. If I will drop the green ball from 50 km/h car to the car which travels 200 km/h, when they will be beam each other, of course, it will apparently be deflected that way. In reality, it will not be deflected. It's just this car will run away from it, technically, yes, speaking. But apparent direction of the ball will be deflected. So the same as here, this is the Coriolis force. It's apparent. I mean, this is real deflection of the air, but this is the apparent force which are happening, which are caused by the different rotational velocities of the Earth. And this is why we have different direction of the winds. Pay attention on this last slide, last picture. You see, this is the low pattern wind. Where we have this Hadley cell, the general direction is deflected to the right in respect to the rotation, yeah, and the pattern is from northeast to southwest. When in the mid-latitude cell, the pattern is westerly, yeah, from west to northeast, and then again over the polar region, again from northeast to southwest. Okay, this is why in Europe, for example, in Czech Republic, the wind, the lower level wind blows so often from the west, because we are located in the mid-latitude cell, in the Hadley cell region. So in Hadley cell region, in Ferrel cell region. So in Ferrel cell, the lower layer wind is going from the equatorial side towards the polar side. It will be deflected where? To the right in northern hemisphere, so which will give us the direction from the west. Clear? Write down me, please, if it's clear. Thank you. Okay. Now about this local wind patterns and what we call the area of high pressure and low pressure. So we have high pressure and low pressure area. So what is the low pressure? Low pressure area is the area where low pressure is surrounded by the higher pressure. I mean, yeah, it's not the rocket science definition, very obvious. When it can happen? It can happen in the areas of ascending air. Yeah, so if we have ascending air that goes up, we will have suction close to the ground. And this suction will take the air away from the Earth, so you will lower the air pressure because the air is being lifted, yeah? And there will be zone of the convergence, yeah? So the area from adjacent regions will be rushed in. That can be caused by the temperature. Yeah, so if you have high temperature, you have ascending of air, you have area of the low pressure. Now we're speaking about low level, yeah, because high altitude profile we already covered, yeah. There is reverse logic. The hotter the air, the more expanded, the higher the pressure at the given altitude. When we're speaking about the, like now when we're speaking about the segment close to the ground, we have this diagram applicable. So when you have this ascending of the air, suction of the air, you have area of the low pressure, like Venturi tube, for example. And everything which is around is rushing in. It's also higher pressure area there because there is no ascending phenomena or the temperature is different. So this is called the low or cyclonic area. Also, it can call depression. You can also have convergence on top and divergence at the bottom. Then you will have high pressure area because that makes sense. If you compress and compress and compress air from above, you cannot, I mean, you will increase the pressure because there is a compression. There is always an inflow on the new air down. It will, yeah, it cannot accumulate endlessly. It, of course, will spread away, but it will spread away. Why? Because you have higher pressure, basically, yeah? Because you try to stuff this air close to the ground. It doesn't want to. I mean, it reaches. It's not that it doesn't want to. Just imagine you have the bag and you start packing the clothes. You pack and pack and pack and pack until it rips off. The same here. Clear? So the area of high pressure is called anticyclone. Where we can find this area globally. So let's look here. At the equator, we'll have area of low pressure. In mid-latitudes, that would be high pressure. Then will be again low pressure area at close to the polar. Lost the word. Polar circuit. I mean, around the area of 60-degree latitude, and high pressure area over the pole. I mean, speaking about the ground, yeah? And vice versa, it will be for high altitude, high pressure over equator, low here, high here, and low over the pole. Okay? Now we finished with the high band. We now getting closer to the ground, yeah? Wind direction and local wind patterns. So what causes the wind? We spoke about this today. The wind is caused by a pressure gradient, unequal differences in pressure per unit of length. So high pressure area has more air molecules, and we already spoke at the beginning that more molecules, more density, more pressure. And the low pressure area, less molecules, so lower pressure, and you have the wind because these molecules simply fight this. They have more energy. They conquer the length of the lower pressure, lower quantity molecules. So this is the direction of the wind. Now, the strength with which this wind is moving is called the pressure gradient force. The difference between the pressure, yeah, the pressure gradient, and the force that arises from this pressure gradient that causes air to move, called pressure gradient force. Now, where this pressure gradient force is directed to? In the area of high pressure, it's directed away from the area of high pressure. Makes sense. In the area of low pressure, it's directed towards, because low pressure is the area of lower pressure surrounded by the area of the higher pressure. Yeah, so you have high pressure everywhere around and low, and it rushes in. High pressure area, high pressure surrounded by lower pressure, so it pushes away. Make sense? Now, the speed. the speed of the wind. So speed of the wind is proportional to the pressure gradient force. The closely packed isobars, yeah, isobars, those are areas of the same pressure, yeah, but the closer isobar spacing you have, meaning that, let's say, this is the lower one is 10 and each subsequent is -5, for example. So this is 10, this is 100, and each subsequent -5. Yeah, this is 100, this is 95, this is 90, this is 85. But here you have 100, 95, 90, 85, 80. So higher, steeper gradient of the pressure, steeper change of the pressure per unit of distance. So, of course, under these circumstances, you will have stronger gradient and stronger wind. So that's why the steeper, the faster the change of the pressure, the stronger the wind. Now, normally, the low pressure areas would be an example of the more closely packed isobars, because think here, like say this high pressure area, yeah, it has to push away it has to push the air away. So the change of the pressure will not be that fast, because I don't know. I even lost in my my own phrasing. Well, it takes energy. That's why. Yeah, like try to. I don't know. Imagine you are in between two, I don't know, cars, and you need to push them and you need to push them away. That wouldn't be that your pressure gradient, yeah, your pressure will not be that, you will not be able to develop such a strong force, and thus like the wind. But if those cars will start moving towards you, they will collapse you very fast. So yeah, this is like very thank you, Jeremy. This is a very childish example, but since the low pressure area is the area which is tried to be attacked from all the sides, the gradient will be stronger. The magnitude will be faster. Yeah, this is the guys. We've tricked you. At the end, you will have the car driving exam, and yeah. I don't know. Today is a car day, apparently. So that's what dictates the speed velocity. However, pressure gradient is only one of three forces. Yeah, I'm already reading here that affect the flow of the wind. The second, the second force and the third force are correspondingly the Coriolis force and the friction force. So we have components of the wind that affect the magnitude. That would be pressure gradient and the friction, and then direction would be pressure gradient and Coriolis. The higher the friction, the slower the speed. Make sense? Makes sense. Because friction, waste of energy, yes, some molecules are hanging with some, I don't know, obstacles, terrain, whatsoever, and then next adjacent molecules are decelerating because of those previous, and so on, so on. So the higher the friction, the less the speed. And we already spoke about the pressure gradient. Yeah, the pressure gradient and the friction define the speed. Now the direction would be defined again by the pressure gradient, because where we have the step from higher pressure to the lower pressure, that way we would have the movement of the air, and Coriolis force. And Coriolis force would be another component which will affect the direction, because we already expressed why. The cars, again. So when those three forces are combined, we would have the certain type of the wind. We may have the geostrophic wind, which blows parallel to the straight isobars, and the surface wind, which would be not flowing across along the isobars willingly. Let's speak about the upper wind airflow, the geostrophic one, the one that blows along the isobars. So why do we have this? Because we have the direction of the pressure gradient force, yeah, let's say from higher pressure to lower pressure. Then, as the air starts moving, the Coriolis force comes into play. The Coriolis force tries to deflect it into the opposite way. Eventually, those two vectors are somehow find the balance, and you have the wind speed which is blowing across along the isobars, and this is called the geostrophic wind. But this slide is depicts it visually. Now, the surface wind, however, would be slightly different, because we will have the friction force, which will decelerate the wind, and so Coriolis force will be able to fight back its positions a bit, and the whole system will be deflected. I mean, will be affected, not deflected, but yeah, affected and thus deflected. Yeah, because we have this additional vector which decelerates the wind, and it's more now pointed towards the pressure gradient force side. This is why in upper air wind flow can be characterized as the air which blows along the isobars, and the direction would be in the areas of the high pressure will be clockwise, and the areas of the low pressure anti-clockwise. Why? Because just all the time imagine the example with these cars. I don't know. Here, in the high pressure area, the air tries to move towards the northern region. Yeah, let's say here, and it's deflected to the direction of rotation, to the right. Yeah, so clockwise. Here, from another side of the high pressure, it deflected towards the equatorial region, but anyway, it deflects to the right again. So you have this clockwise rotation. In the low pressure area, from the top of the picture, it goes towards the area of low pressure, it's deflected to the right, and from the bottom of the picture, it goes towards the area of low pressure, it deflects to the right, and you have anti-clockwise rotation. Yeah. In lower air flow, we have like technically the same. However, because of this friction, the air is moving slightly more into direction of the pressure gradient force. No, it can be there can be different reasons, but normally yes. I would say normally yes, but not all the cases. Because if you have convergence on top, and like if you have some movement in the atmosphere that makes the air to ascend, you may have pretty hot air, which will create the high pressure. This is adiabatic cooling, actually, but this is the topic for the second class, because today we will not make it. So don't stick to this simple pattern. Cold means high pressure, not all the time. You may have very hot air, but high pressure. In the surface friction, we have air modified slightly into direction of the pressure gradient force. And this friction layer is typically found at the altitude from 2,000 to 3,000 feet above the ground, above the surface. What is the next slide? Okay. As the last slide, I think, for today, let's look at the windy. Oops. I mean, I could start the windy on itself, but let's watch the video. So this is the area of the low pressure and the area of the high pressure. Yeah, it's written low, high, consequently. Note the spacing of the isobar. Here you have 1014, 1016, 1018, 1010. Yeah? Is it visible to you? So the gradient is pretty strong. The gradient is pretty strong. And the wind speed, you see, is faster. Yeah, these white traces are like showing you the magnitude also. So the speed around the low is faster than around the high because due to the reasons explained before. They also note the pattern of the rotation. Yeah, area of the low pressure rotates anti-clockwise, area of high pressure rotates clockwise. Everything as we said. You can play with this and windy, yeah, at windy by your own. So again, another high pressure rotates clockwise and low pressure anti-clockwise. In southern hemisphere, that would be vice versa. Because, I mean, in southern hemisphere, if in northern hemisphere everything is deflected to the right, in respect to the movement, in southern hemisphere everything deflects to the left in the respect of the movement. So this is why in southern hemisphere we would have vice versa, high pressure areas rotating anti-clockwise, low pressure areas rotating clockwise. Yeah, because air wants to rush. Let's find the low pressure. Yeah, air wants to rush in from the area of the higher pressure to the area of the lower pressure, and it's deflected to the left because the rotational velocity of the area which is above, closer to equator, is faster. So this ball just doesn't hit this area and flies away. Yeah, so this is why you have deflection to the left. And of course, if we will scale out, if we will change, so this is at the surface, yeah? So this is at the surface. If I will climb to flight level 340, I would even see the jet streams. Yeah, here's the white areas are like the areas of the higher velocity. You see 102 knots, 101 knot. So the jet streams are pretty fast moving currents of air. This is why flying from America to Europe is faster than from Europe to America, because you fly with tailwind from US and you fly with headwind to US because of the jet streams. If you paid attention, the last jet streams were not super accurate as they were on our slides. Well, this is because, again, this one thing is the model and another thing is the reality. Yeah, the polar jet streams is shattered. No, polar is not that shattered. No, polar is shattered. Yeah, because many of segments of this polar jet stream goes over the water, and there are not that many steep gradients, and some areas are like some water currents are hitting area from below, and some continents receiving more insolation. So there is no uniformity as on those models that we were discussing before. However, like general logic still works, and you saw the direction they were to the east, from west to east. Okay, guys, I'm opening the attendance one more time. I'm opening the attendance one more time. I hope now it will work. Now I opened. You please click it, and let's do the task number 3. And task number 4, okay, 7 questions. Okay, good that it works. 7 questions, come on. 5 more minutes to invest, to spend for the sake of the knowledges. And wait, I think, well, okay, let's do. I think it should be fine. If already confirmed, then it means it was confirmed before. So hopefully it's fine. If it didn't work, don't worry. I will. I mean, we also have the tracking of the. Okay, thank you for letting know, Hassan. And all Hassans, thank you for letting know. That's fine. We will make. I'll make a recording of this screen. So. You know, then in this case, after you finish with this task, there are only 7 and they're not complicated. Just write down the name of the. Okay. Guys, is there anyone who doesn't have 10 more minutes? Okay, then this is the plan. We do worksheets quickly together, not more than 10 minutes. And then at the end, but please, just at the end, write down all your names and surnames, okay? I mean, cool? So this is how we will be able to check. That would be extra step. Okay, let's go. The troposphere is the troposphere. Come on with me. So just 1, 2, 3, 4 in comment section, yeah? So what is this troposphere? Help me. Okay, boundary between stratosphere and the troposphere. Okay, no. 2. Okay, but it changed. So it should be the part of the atmosphere above tropopoles. No, below tropopoles. Yeah. Below tropopoles. What is the primary cause of all changes in the weather? Movement of warm air masses to the sun. Variation, changes of air pressure. So one more time. Now 1. Yeah, variation of solar energy. Yes. Okay, then the atmosphere is heated. Okay, 3334, Hassan. Okay, the atmosphere is heated primarily by terrestrial insolation from the sun. No, insolation from the sun. No. So terrestrial radiation released by the Earth. Yeah, that's our yeah. Thanks. That's our option, of course. Now what generates air movement and the cause of the wind? Basically, duplicating the question. I know, Tamer. So we have okay. Our opinions are now separated. So we have either pressure or difference in temperature. What generates the movement, the air movement? Welcome to ATPL questions, actually, because be careful. Pressure. What pressure? Pressure difference. If that would be pressure difference, then yes, maybe. But there's just pressure. But pressure by itself doesn't create movement. The difference in something, and difference in temperature, which then create the difference in pressure. This is yes. Okay, what causes the surface winds to flow across the isobars at the angle rather than parallel to isobars? The greater density. What causes the surface winds to flow across the isobars? Two. Of course, weight. Thanks, Duncan. Across rather than parallel. Where we don't have friction, then we have parallel movement. But this slide, remember the last slide. Once we introduce the friction into the system, when we introduce the friction into system, it moves across. Across. Okay. Okay. Okay, now we need to think. Now we need to think. These are two tough questions here coming. On the left. If you fly a tailwind in the north, yeah, that's guys. This is actually a good mnemonic or whatever pattern. Yeah. So if you are in the northern hemisphere with the tail from behind, tail towards your back, your low pressure area would be. That's fine, Jeremy. We figured out that we will write our names at the end just to double check, you know. I mean, just to make sure that everyone is encountered as the present. So on our left, yeah, because in anti-clockwise movement in the area of the low pressure, yeah, you are standing, wind blows to your back, the low pressure on your left. Or if in high pressure system, clockwise movement, wind blows to your back, and from the left will be, on the left will be the low pressure area. Yeah, that's clear. Yeah, and okay, look at this picture, like upper left picture. Yeah, the wind blows towards your back, the lower pressure will be always on the left. In the northern hemisphere, in southern hemisphere would be on the right. And the last question, okay, let's think here. Okay, so we have, you are flying east to west in northern hemisphere. Okay, let's think here. You are flying from east to west, let's say from Prague to New York in the northern hemisphere along 500 feet hectopascal, 500 feet, 500 hectopascal pressure level. So something approximately at 18,000 feet outside of the friction level layer. Pressure surface. Which of the following statement is correct? Why this question is right? If the wind is from your right, you are gaining altitude. Let's check here. So we are flying from the east to the west. Yeah, so we are flying. Which picture I should take? Yeah, we are flying. Wait, one more time. What is the, if the wind from your right, you are gaining altitude. You are gaining altitude. So we need to go to the area of the higher pressure. Yeah, we are going to the area of the higher pressure. We are gaining the altitude. So to the hotter, wait, sorry, just confused myself a bit. From the right, we are gaining altitude. So I need to go. Okay, let's draw quickly. Let's quickly draw. The only condition under which it can be true is that we are gaining altitude following the same pressure layer, pressure. So we are going to the area of the hotter air, and here is cold. Yeah, because that one is 500 hectopascal isobar. Okay, hot air. So we have hot air ascending. We have low pressure here and high pressure here. So if it's the high pressure, this is the northern hemisphere. So this is the high pressure rotation we have clockwise. This is the low pressure rotation anti-clockwise. We are flying and the wind is coming from the right. Okay, in between them, what do we have? How they connected? Sorry, my head just stopped working. Okay, let me draw extensively. So it's like this and like this. The wind is coming. Are we going from the east to west? Guys, this definitely makes some sense, but I don't know. I just you know, I have some lock, mental lock. From the east to the west in the northern hemisphere. Wind is from the right. I'm gaining altitude. I'm gaining altitude because my isobar expands. So that should be the. Okay, that's the good point, Duncan. Well, you know what? On the next uphill, yeah. Yeah, uphill. You know, the thing is that we can gain altitude only if we will get into the area of the hotter air, right? Make sense? Makes sense. So because the isobar is expanded in the hotter air, so the hot air will be here represented by the. Okay, now look the trick. Now look the trick. The thing is, guys, it's everything is relative here because this is now I'm speaking about the it's about the ground. Yeah, over let's say where I can answer this question. Yeah, now I remembered myself. So we are now this is the diagram respecting to the ground. Yeah, on the ground that would be low air, a low area pressure, but on the if we will go up, it would be higher area, yeah, because of this expanded column. So this is actually the hot, this is the hot. This is the high pressure area, and this is the low pressure area, yeah, because the column here is that big. Here the column is that big, smaller one, but both of them have 10 at the bottom, yeah, and 0 at the top. So let's say at certain altitude, let's say at 500 feet, to 18,000 feet, you will have, let's say, 6 units of air, not 6, but maybe, I don't know, 4 units of pressure here and 1 unit of pressure here, because here it's close to the top, to the 0, yeah? So this is actually will be the high pressure area aloft. Aloft, there would be a high pressure area in the column of the hot air, yeah, as we saw on these boxes, on these columns, yeah, before. So, and if it's hot, you need to delete this. If it's hot, if it's high pressure, this is high pressure. So high pressure area rotates clockwise in northern hemisphere. Yeah, clockwise. This is clockwise. This is anti-clockwise. This is clockwise. So this is clockwise. Come on. And this one will rotate anti-clockwise, the low pressure area. So yeah, and we are approaching this area. The wind is blowing from our right. So we are meaning that we are reaching to the area of the higher pressure, which is caused by the expansion. And our altitude, we are gaining the altitude. Okay, got it. But yeah, it's like for gliders also, but we are now speaking about the pressure more. But yeah, hot air rises. This is also for the gliders. Guys, got it? No, seriously, got it, because it's important. Okay. Here, this picture, this slide. You have higher pressure. Can only be moving then to hot. Yeah. Because yeah, hotter air. The pressure at the given altitude is higher. I mean, the wording is a bit tricky because you need to know to which altitude certain pressure level corresponds. But if 1000 hectopascals at the bottom, so 500 hectopascals, it's definitely not close to the ground. It's somewhere, according to that slide with atmospheric layers, it's like 18,000 feet. It's somewhere like middle altitude range. Yeah, so at altitude in hot air, you will have higher pressure. Hot air, high pressure rotates clockwise. You have the wind from the right as we draw in the picture, and thus you are gaining altitude as on this slide, or on the picture from your classwork, the one that from altimetry, this one. You are gaining altitude. Okay. Thank you. Sorry for the delay. I just wanted to give you the knowledge as much as possible. Write down your name and surname, and again, sorry for the delay. Have a good evening. You're welcome.
Have a nice weekend.
Thank you, Duncan. Thank you, Andrew.
Have a good night, everyone.
Thank you. Thank you, Alan. Okay, I'll send you. Jeremy, I'm not sure that worksheets will be working after the finish of the class. There is some time frame since like within which they can work. I will send you the link, like when we will stop having the comments, yeah, so it will not get lost. Try to open it, maybe. Yes, Leonidas.
I've got a question about the exams. I don't know if you might be able to answer it. The thing is, the platform's been very problematic in the past 2 weeks, and especially for the big day that was the stage 1 exam. It said that I was not invited to do the oral check, the oral test, because I did not supposedly finish some exams, which I did, but I don't know if the platform like recognized them.
I can relate that if like the exams. I mean, it's
the stage 1 exam.
Yeah.
Yes.
Did you attend it?